Purpose of this video is to go over goal 15 of our inference unit. The goal here is to be able to perform a paired t-test and find a confidence interval for paired data. So the good news is, as far as the AP exam goes for coronavirus, this is the last lesson. So if you've made it this far, this is the last new stuff you have to know. What's this about? Well, we've been doing a lot of inference. We started with one proportion and then worked with two proportions. We made confidence intervals and tests. Then we moved to means. We did one mean and two means, and also did confidence intervals and tests. Basically, in all of those procedures so far, everything had to be independent. So whenever you were working with the data, one piece of data had to not affect another. If you had different groups, one group had to not affect another. So the paired t-test and paired t-interval have the qualification that they actually allow for the data to not be independent. At least what's going to happen here is we're going to have essentially what would normally be a two-sample situation. And we're only going to do this for means. You don't have to worry about proportions. We'll have a two-sample situation where we'll have two lists and two means, but since the data isn't going to be independent, one list isn't going to be independent from the other, we're actually still going to be able to come up with a test and a confidence interval. So that's what this paired data stuff is about. It's basically looking at what happens if we have two sets of data, but they're not independent, all right? So when we have sets of data that are not independent, they're referred to as paired data. So namely, paired data is two pieces of data that are linked. That is, they are not independent. Lists can be made of this kind of paired data. So if we wanted to see some examples of what might be paired, we're looking for two lists of information, but the lists or the members of the lists are not independent. So example one says, say we were to list the incomes of men and women who are married, so husband and wife, heterosexual couple pairs. It would turn out that, men and women aren't randomly put together. Men and women marry each other for a reason. It's not hard to believe, too, that, studies have shown that people who make more money and who are more educated tend to marry other people who are similar, who earn more money and who are more educated. All right. So the case of men and women who are married, if we looked at their incomes, they wouldn't be independent of each other. These people picked each other for some reason, and income might be part of that, or some other factor might be part of that. The second example is weights of subjects before and after treatment. So say they wanted to try a new weight loss drug, and they recruited a bunch of people. Before and afters are great examples of paired data, because my weight before I do some treatment, and then after maybe I take some chemical or I do exercise or something, those weights are not independent. Basically, those weights are befores and after of me or a similar person, and since they're before and afters, they're linked together. They're my weight after is dependent on me and my body and what I was before. So before and afters are great examples of paired data where the data clearly isn't independent because it's before and afters of the same item. The last one mentions, number of points scored by each partner in doubles tennis. Just similar to the married couples, you don't just randomly pick your doubles partner. There's usually reasons why you have the partner that you do. For example, a champion tennis player probably wouldn't choose me, a novice, as their doubles partner. They would probably choose someone who they got along with and who was also of equal skill or similar skill to them. Who also has similar background. They might even be similar ages, and due to segregation in the sports, they would probably be the same sex as well. So, you wouldn't see in professional sports a man teamed up with a woman. Unfortunately, I don't know why they don't do that, but anyway, so these are three examples of paired data. So basically, if we had two lists of data under these conditions, we wouldn't be able to use a two-sample t-test, because a two-sample t-test requires that the groups be independent. So what if the groups are not independent? Well, That's what these things are about. We can do either a paired t-test or a paired t interval. So how do we perform these? The good news is it's basically a mix of ideas from the two sample procedure and the one sample procedure. So testing paired data, the first part says, since paired data is not independent, the genius of this is that we can actually treat it as a single measurement. So instead of working with the two pairs of data and the two lists, we can actually combine them to form one list of data. So that's kind of the smart thing about this. So the second part says how we do that. The single measurement we use is not from the data itself, but it's the difference between the data pairs, because this is what we care about. So, or when you see the example, you'll see that's what we're looking for. So instead of making, for example, in the example of husbands and wives and their income, instead of making a big list of the husband's income and analyzing it, and then making a big list of wives' income and analyzing it, what we would do is take each husband-wife pair, we'd subtract what one makes from the other and find the difference. Like, what's the difference between husband and wife pairs? Each one of those pairs will create one data point, the difference between them, and then we'll make a single list of those differences. So then this makes a single list of data, so we're going to treat it like a one sample procedure. So I think I put in terms of tests, but this is true of intervals as well, confidence intervals. So it says, once we have our list of differences, we basically have one data list now. We treat this list as if it was a one sample t-test, or if we're making an interval, we would do a one sample t-interval. So the bold here sort of sums up what we got. What is a paired t-test or a paired t-interval? It's just a one sample test or interval on that difference of pairs. So we're taking two sets of data, subtracting them into one set of data because they're linked, and then doing a one sample procedure on it. That's basically what this is going to be about. Like with everything we do, we need the conditions met. Most of the conditions you'll be familiar with, but clearly when we did both two proportion procedures and two sample mean procedures, we always needed the independent groups condition. Now, the whole purpose of this procedure is not to have independent groups. So like, what if they're not independent? So we replaced the independent groups condition, which we're obviously violating, with the paired data assumption. So this first condition is new. It's basically if our data is not independent, so that's what it says here, pairs of data must be related, that is not independent. And same size lists aren't enough. Be careful if you're taking the exam that just because lists are the same size doesn't mean that they're paired data. You can have independent things that we just happen to take the same sample size out of. But paired data will be the same length. But make sure that the data is linked in some way. So, for example, like the tennis pairs, they're linked together. Or the befores and afters, they're linked together. So long as you have paired data, you can use this procedure called, the paired t-test or paired t-interval. Now, independence is still involved. We don't have independence of groups, meaning like a husband and wife are not independent of each other. But we need each pair to be independent of each other. So that's what this next condition is. Basically, each pair has to be independent from other pairs. So like in the example here, a husband and wife aren't independent of each other, but their couple must be independent of other couples. So when we pick a husband and wife, we want to make sure the next husband and wife is independent of the original one. All right. So the pair itself is not independent, but the pairs compared to other pairs have to be independent. So make sure you got that idea. All right. And then there's the classic other ones. Random. We always need randomness. Basically, the pairs must be picked randomly. If the pairs are befores and afters in experiments, we must make sure that the treatments are assigned randomly in a way that's representative of the population that's being studied. All right, so randomness is still necessary within the pairs. Once again, the 10% condition, they usually don't talk about this a lot in these procedures. It doesn't apply to experiments because experiments are self-contained. But if you're doing samples where you're trying to represent the population, you want to make sure your samples are not too big. And then that nearly normal condition. So being that we're considering the list of data as one single object, we're not going to have to check the list size of two separate things. We just basically those list sizes should be the same anyway. We just need to know how many pairs we have. So the nearly normal condition says, like we've always had before in these other procedures, that if we have more than 40 pairs, the central limit theorem will kick in. Our sampling distribution will be very, very close to a t-curve or a normal curve, and we won't have to worry about things unless there's some kind of extreme case. The thing that we usually have trouble with is if there's fewer than 40 pairs. Like anytime we're under 40, the central limit theorem hasn't kicked in enough to overcome really skewed data. So if it's under 40, we do need to check the original data to see if it's unimole and symmetric. Now, it does tell you which data to check. The original data, meaning if I was looking at the list of husbands and wives, I wouldn't need to see if the husband data was unimole and symmetric and the wife data was unimole and symmetric. I would just need their difference pairs to be unimodal and symmetric. So after you subtracted the two lists to make one list, that one list you would have to check. If you're under 40, you want to make sure that the original distribution data is roughly unimole and symmetric. If that's the case, then the central limit theorem will still work, and you'll get your sampling distribution to be roughly normal, usually a t-curve. All right, so still check the nearly normal condition. All right, so let's talk about the confidence interval first, and then we'll move on to the test. So the paired t interval, if the data is paired, first we have to find the differences of all the pairs. So I just mentioned doing that. You need to go through, if you had separate lists, and go through and subtract them. Now, typically, they'll give you this information. A lot of times they'll do the work for you or give you a summary of the information. But if you were doing this by hand from scratch and didn't have anything to start with, you would get your pairs of data and you would go through and make a new data list where you subtracted one value from the other for each pair in the same order until you had a new list. So once the list of differences is made, we now have a single list. We can use it to find the mean and standard error for the sample means. So this one list is going to have some characteristics to it. The single list is going to have its own mean. So this difference list that we made will have some average difference. The average difference is called D bar. So the bar means the average, and we take the average of they use D for difference. So the mean of this data is referred to as D bar. It's the mean of the difference list. And then the difference list will have its own standard deviation. That's called S sub D. Now, when we go to do inference, remember, we want the standard error, which is not the standard deviation of the data, but the standard deviation of the sampling distribution curve. That meant if we kept taking samples over and over and over again, what would the samples look like? So realize in this case, S sub D is the standard deviation of the original difference list. If we want to make the sampling distribution for how the samples come out, we then get the standard error of the difference list by taking the standard deviation of the list and dividing it by the square root of n, where n is the size of the samples. All right. So keep in mind there's the mean of the list, the standard deviation of the list, and then the sampling distribution's standard deviation was referred to as the standard error because, once again, we're estimating it. We don't have the population standard deviation difference, so we're using the sample to estimate it. So then we can make the confidence interval with this information because the confidence interval always has the same structure. It's our mean that we found in our sample, plus or minus the t star, which is how many standard deviations to go out for a certain confidence level, times what that standard error is. So notice the structure is the same. We just need d bar, the standard error, and then we've handled this before. The good news is, since it's essentially the same as a one sample procedure, we don't need that weird degrees of freedom So we're treating it as if it's one list. Our degrees of freedom's back to n minus 1. And always keep in mind, just have the extra note here, that the t-scores determined by the desired level of confidence and the n value. So basically, we're going to do n minus 1 degrees of freedom, and then it's based on what confidence we want. Typically, it's 90, 95, or 99, but they could do other ones if they wanted to. All right. So let's do finally an example. So this one, I think I took this out of the book. Kind of interesting. Speaking of husbands and wives, I didn't have data on their income, but I did have data on their ages, at least of British couples. So this is asking how big is the difference between the ages of husbands and wives. Now, it's probably common knowledge that, at least it typically seems that husbands on average seem to be older than their wives. That doesn't mean that there aren't some women out there who are much older than their husbands. Most people are pretty close in age. But typically it seems that on average you see, usually the man is a bit older than the woman in heterosexual married couples. In fact, I'm married and I'm 3 years and 1 month older than my wife. So I didn't choose her because she was younger than me, but hey, I guess it just turned out that way. All right. So our question is there some kind of difference? If there is, could we put a range on it? So they took a sample. Obviously, to do a census of all these couples would take forever. So they pick 170 British couples, and these people provide their ages. And here's some of them, because basically to look at 170 data points would be ridiculous, but you'll get the idea from looking at some of them. So in the first column, if I can get this right, the first column is the wife, and the second column is the husband. So as we go through this data, we see couple 1, the wife was 43, the husband was 6 years older at 49. In the second couple, the wife was 28, and the husband was actually younger, he's 25. Third couple has the wife 30, the husband 40, 10-year difference, and so on. Basically, since the intuition is we're thinking the husband is older than the wife, I decided to do my difference list as husband minus wife. So in this case, I took 49 minus 43, it's 6. Now here, since the husband's younger, the negatives just represent when the wife is actually older. So 25 minus 28 is negative 3. So the wife was 3 years older. You can go through and do this. So here the husband's 10 years older, the wife's 5 years older, 6, 5, and 9. Husband being older, and so on. So once you get this idea, we don't need to go do the whole thing because someone did it for us, but there'd be 170 of these pairs. We'd have to subtract these 170 times and get this difference list. The good news is we never look at these again. We just look at this list. Now, the good news on top of this is somebody already compiled the data for us. So pretending we had all 170 pieces of data, what we would do is we would, put in that one variable stat, or usually let some kind of technology do it for us, and we would find out the mean difference is 2.2, meaning what they found of these 170 British couples is that on average, this difference list comes out as 2.2, meaning the husband is on average 2.2 years older than the wife. What's the standard deviation list? 4.1. So the spread is kind of large. So within one standard deviation, we could go up and a husband would be about 6 years older than his wife. That's not too unusual. But going the other way, it's not that unusual either. Going one standard deviation down from here would place the wife about 2 years older than the husband. So even though on average the husbands are older, the spread, at least on this list, shows that it's not completely uncommon to run into the opposite situation where the wife is older. All right, but we have a sample of 170 people. So we want to use this data to find out if we kept taking samples of 170 people, what does that look like, and what does that mean for the entire population of British couples? So I'm going to show you how to create a 95% confidence interval for the actual difference in the age of British married couples. We know our sample has a difference of 2.2, where the husband's older than the wife. But once again, that's our sample difference. What does that mean about the actual population? So it's difficult to study the entire population, but from this 170 couple sample, we can infer a range of values for what the population is. And then we can use that to see, well, are husbands really on average older than their wives, or is it possible it goes the other way around, or maybe it's 0, maybe they're the same age. We can find a confidence interval to help us answer those questions. So the first thing when doing any of this is to check the conditions. So I'm just going to do that verbally as usual because it takes a while to write them out. So let's go back to the conditions real fast and check them out. The pair day assumptions definitely met. We have husband and wife pairs, and they're choosing each other for a reason. Not to say it's completely impossible, but most 20-year-old people don't marry 90-year-old people, right? Like they're paired up for reasons. Like when I was looking to get married, I wasn't looking for somebody who was 90 years old. So you're more likely to pair up with somebody who's similar to you in certain aspects. Age is one of them. All right. So we definitely have paired data. Do we have independence of the pairs? Well, we'd have to sort of trust that people did their job correctly with the randomness and all that stuff. But there's no reason to believe in the samples that one couple's difference in age affects another couple's difference in age. All right. Like when I married my wife, I wasn't looking around at other couples going, oh, I need to, match what the neighbors did or something. So we have independence of the pairs. Not, the pairs together are linked, but from pair to pair, they're independent. Hopefully I'm saying what I mean. All right. Random, once again, in a AP problem, they would give you more information. They would probably either tell you who did it or that they did it randomly. We'll just assume that whoever did this 170 sample did it correctly and that they did it randomly. So we'll trust them. 10% condition, 170 couples is surely less than 10% of all the couples in Great Britain. I mean, there's millions of people in Britain who are married, so 170 couples is not taking too many. And good news here is the last few examples I did, we had to check this nearly normal condition. The good news is that since we're at 170, we don't really have to worry about looking at the histogram of the differences of the 170 pairs and all that stuff. What we can do is just go, hey, it's over 40. And this should be good to go. We should be able to get our sampling distribution to be a normal curve / T curve because the central limit theorem would kick in and those samples would come out pretty much looking unimodal and symmetric in the like I said, in the shape of a normal or T curve. All right, so conditions are checked. So let's create the confidence interval. So behind here on the magic board is the confidence interval. So since we've done these procedures before, hopefully there's not too much new to go over. Basically, I did mention check the conditions. That's what I just did verbally. Here's the data we need. We need D bar, which was the difference between the wives and their husbands, basically husband minus wife. We found on average that was 2.2 years. The standard deviation of that list was 4.1 years. The sample was a sample of 170 people. We're looking to make a 95% confidence interval. That's going to come in for the T-star. And we need the standard error calculation. So basically, if we keep taking samples of 170, based on this sample, what would the distribution look like? Well, the standard error tells us take the standard deviation, 4.1, divide by the square root of n. Our sample size is 170. So for sample sizes of 170, how spread out will they be? Their standard error is 0.3145. All right, so make sure you know the difference between the standard deviation of the original list and the standard error, which is the spread of the sampling, the difference of samples of 170. All right, so with all this information, we can start filling in that confidence interval. The confidence interval says take our point estimate, which is 2.2 years, and we found that for our sample. We now want to capture the real value of the population. The sample's not expected to be exactly the same as the population, but it's expected to be close within reason. So how close is it? Well, this margin of error out here tells us how far we need to go out to capture it with 95% confidence. So we know D bar is 2.2. We know the standard error from that calculation is 0.3145. The last thing I need is T-star. Well, remember, T-star tells us how many standard deviations go out to cover 95%. Well, I know it's 169 degrees of freedom because it's n minus 1, which is 170. So the way I'm going to find that is, since I want 95% confidence, that's down here in the red. If I want 95% confidence, I can find out what the T-score needs to be. But remember, I need to do that trick that we keep doing. I need to take the 95 cut it in half, that's 0.75, and then add 0.5 to it. This is the number that you need to put into the calculator in inverse t. Remember, inverse t gives you how many standard deviations you need to go out to cover this area on both sides. So basically, I put in this area, because inverse t won't work from the middle, it works from all the way from the left. So this gives the number all the way from the left, and we don't have to worry about the number from the middle. So using this number, we inverse t this with a curve of 169 degrees of freedom, and I get 1.974